Hi, welcome back. In this lecture, I want to continue talking about the complex numbers, and I want to focus on two important formulations, the Cartesian and the polar description of complex numbers. During this quantum computing course, we will see that we can express quantum computing states using complex number, and we will switch from Cartesian up to polar description and vice versa. So we need to get comfortable in using both a formulation. So let's start with the first formulation that is called Cartesian description. In the Cartesian description of the geometry of a complex number, we use a so-called complex plane or Argand plane. In the complex plane, we represent our complex number using a plane where on the x-axis we have the real magnitude and we have the imaginary part on the y-axis. So pairs of reals corresponding to a point on the plane correspond also to vectors that start from the origin and point to that point. So this particular point here represents a complex number with A, that is the projection on the real axis, and then B, that will be our imaginary part. So when we use the Cartesian formulation of the complex number, we will have that the length of our point, in this case 3, so it's 1, 2, and 3. This will be the real part here, and then we are going to have the imaginary part that is 1, 2, 3, and 4, that is going to be here. So this is the imaginary part. So this vector here represents our point, our complex number 3 plus 4i. The length of this vector with the origin in 0, 0 is going to be the modulus. So the modulus is the length of the vector representing our complex number. The square root of the sum of the square of its edges will be precisely the modulus as defined in the previous lecture. If we try to calculate the length of this complex number of this vector, what it will be. So in the previous lecture we saw that the modulus of C is a positive number, and then the square root of 3 plus 3 square plus 4 square, and this is equal to 5. That is a simple calculation. So far we have seen this Cartesian description that represents any complex number as a point on the so-called Cartesian diagram, where we have on the x-axis the real component and the y-axis we have the imaginary part. So this is very similar to what we saw in the previous lecture. An equivalent description of our complex number is to use, instead of the x, y description for the Cartesian, is to use two numbers, in this case an angle, the so-called theta angle, and the magnitude of this vector. So we still use a complex plane, but instead of using the x, y coordinate in this plane, we use two equivalent numbers to represent the same vector. To repeat, we're going to use an angle, theta, and then the magnitude that typically we call as rho. So anytime we can switch from Cartesian description to polar description of the complex number. So if we have two numbers, A and B, that represent the real imaginary part of the complex number, that correspond to the Cartesian description of the complex number, we can calculate first the magnitude using just the Pythagoras theorem, as we did at the beginning of this lecture. So the magnitude, or rho, will be the square root of the sum of the square of the real part plus the imaginary part. Then the other part, we need to have the angle theta, so we can calculate the angle as the arcotangent of the factor, where at the denominator we have b, that is imaginary part, over 8, that is the real part of our complex number. So it's important that at any time a given complex number, we can be switched back and forward from Cartesian to polar description. So let's see, for instance, an example here. We have a Cartesian description of our complex number C that is going to be 1, 1. This in Cartesian description is a vector that is this form here. So the real part is going to be 1, A is equal to 1, and then the imaginary part is going to be plus 1. So this is the imaginary part, and this is the vector that is identifying the complex number in the complex plane. At this point, we want to calculate what is the magnitude, as this is very simple, right? So the magnitude is going to be the square root of 1 square plus 1 square, that is equal to the square root of 2. At the same time, we can calculate the second part of our polar description of this vector. So we calculate rho, that is equal to 1, and we want to calculate what is this angle identified our vector in the polar description. So this angle is going to be here. So we know from the previous slides that theta is equal arcotangent of B, the imaginary part, over A, the real part of the number, so it's 1 over 1. If we take the arcotangent of 1, and this is going to be pi over 4 radians. That is this angle here, pi over 4. This theta is also called the phase of the complex number. It's very important to note that the complex number has unique polar representation only if we confine the phase between 0 and 2 pi. In fact, two complex numbers in polar representation will be identical if their magnitude is the same and if the angles are the same modulo 2 pi, right? So if we have a pi over 4, the phase, and then we have another number with the phase pi over 4 plus 2 pi, this will be the same phase. So we will confine theta between 0 and 2 pi. So we saw that when we have description, a Cartesian description of our complex number, we can switch to the polar description, but also we can do the opposite. We can go from polar description to the Cartesian. So in this case, for instance, if we have rho and theta, we can calculate our Cartesian representation of the complex number as rho multiplied by the cosine of the phase, and then we can calculate the imaginary part of our Cartesian representation by taking I multiplied by rho multiplied by the sine of the phase representing our complex number in the polar description. Extremely important is to know this Euler formula that connect the cosine and the sine multiplied by the imaginary part and the exponential of an imaginary part. So this is important formula that we also will use in this course that we need to know very well. So the exponential of imaginary part multiplied by a factor, in this case theta, because it is corresponding to a phase in polar description, is equal to the cosine theta, and this will be the real part, what we call A, plus imaginary part that is the sine of the phase. So this is the last slide of this lecture, and we will keep working a little bit more on the complex number in the next few lectures. Talk to you soon.